There you are, watching another tutorial video for thinkingParticles 7.3. In this tutorial video, we will learn how to use the power of OpenVDB together with MEL, our latest scripting language we implemented in thinkingParticles 7.3. OpenVDB is a really powerful framework that allows us to manipulate and create volumes inside of thinkingParticles, and we can treat these volumes like simple particles. This is a very unique and powerful feature. No one else offers this, treating OpenVDB volumes exactly like particles. Let's dive right in and see how we can use that and how we can implement that. So in this scene, we can see that we have two objects and the thinkingParticles helper up here. So we have this torus and we have this container, or how is it called, the oil tank object. So I just place these two objects in there and we will now explore what we can do with that. So I want to use those to position particles inside of these objects. So let me now bring out our thinkingParticles user interface and have a look how we set up the scene. So the first thing I did here is bring in our 3D Studio Max objects and turn them into particles and assign the shape or mesh information to these particles as well. So I store them in the VDB particle group. As we can see here, we have the VDB particle group here. So we bring in the torus and the oil tank. Both are stored in the VDB particle group. The next thing is, and watch the hierarchy here, that's important. The first thing we do is we define our container, our volume container, where we say, okay, I want to have a distance field. So this will create or prepare us for a volume we want to fill with data that is an SDF or distance field. Next thing we do is we turn our meshes into real true volumes, and we do that by using the node shape to volume. And all we need to do is we need to supply our OpenVDB container. We need to tell the system where to grab the meshes, and then we need to tell where should we store our field data or grid. And we tell it, okay, store it in the distance field that we prepared here. And it's of type signed distance field. So that's all we need to do. One other thing we might want to consider is let me just turn that into a different scale. So I have deactivated the show VDB, but now I'll turn it on and we get the representation in the viewport what thinkingParticles and OpenVDB has created out of the objects we supplied. So keep in mind we have the original objects still in the scene, and we brought them into thinkingParticles and turned them into particles and get the meshes. And now the shape to volume can rasterize these meshes and create the voxels inside of these fields. The resolution we can control with this parameter here. So now I have a scale of 5, and we can see now we have a really rough representation of our objects. When I turn this lower, we get a much better surface representation and volumetric representation of our object. And we can even dial it up a little bit more, and now we have a lot of voxels inside of these objects. So we can work with either version or either resolution. So let's just, for the sake of this tutorial, start with a more coarse resolution. Let me set that to a value of 2, and I'll now turn off the show VDB node. Next, let's activate the MEL node. And now you can see what I did here is I created particles now. So now we have the particles here. Each voxel or center from each voxel, we placed a particle. So how did we do that? How did we use the OpenVDB data, find out where is the voxel, where's the center of the voxel, and then create a particle and place it in there? So let's have a look on our setup here. What we have here is we have a time interval that just turns on at 0 because I don't want to have it animated and create more and more particles when we do a simulation. So I just set that to activate this one time at the beginning. Then we have the get grid. So I'll just grab the OpenVDB grid, the fields we have created out of our torus and oil tank, and I feed that into the expression MEL. And also the expression MEL has a group input. And the group input is for where would I want to store my particles that I create inside of MEL. So inside of MEL, will access this particle group I specified here. So let's have a look now. And that's all we had to do. Very simple, straightforward code. There's actually one line of code that creates the particles right in the center of the voxels. So it's beautiful, fast, and fully parallel processing of all voxels. So we can really have a huge amount of voxels and a huge amount of data and process it still very fast. So how does it work? What we have here is our inputs. These are the field and the group. Field and group are inputs. One is the distance field, one is the particle group. And then we are right at the code we want to use. I just test a value, and that's the field in value. So we have to understand that our input is called field. So what I want is field in. And that's the data that comes from our OpenVDB field. So I'll grab this value inside of the voxel and I'll look at the value of the voxel. And if this is smaller than 0, we are inside of the volume, because right now I only want to create particles inside of the volume. So I'll grab that and tell it, okay, if we're inside of the volume, please create a particle. And once more, the group, we called it group, input description group, that's our access to the particle group we have here selected outside. So now we store in this group, we create a particle and store it there. And where do we get the position? Because we are accessing in a parallel way and our first input is the field, we have the world position of each voxel running through our expression MEL script. So I get the position from each voxel and I use the create function to create a particle. And if I wanted to know what parameters and what does this function, I can always have the selective help button. And then when I click that, it will bring up a browser. And then with this browser, I can just check and get my online manual. And I'll see, okay, these are the parameters I can supply. This is how I call the function. And this is what's happening. So it's very easy to get started and do amazing things inside. But before we move on to our next idea, because what we have here is now the particles in the center. And when we're going and create our surface, let me just bring in here, we use the OpenVDB shape that just grabs the particles. When I just select it, I grab the particles and create a surface. So when we restart our simulation here, we will see that we get our particles, our surface here. And because we have this coarse volume rasterization, I'll just go back here and we'll change our volume raster. And there we go. Suddenly we have our surface visible. And this is because, let me just go back here. That's because, let me turn that off again. Now we have a lot more particles next to each other, and then our surfacer, as we have set up the surfacer, is able to create the surface between these particles. So that's our basic setup, but we can already see that our surface doesn't look really that great. So especially when we take into account, let me just move that a little bit up, our oil tank. So that doesn't look too great. So what can we do about that? We could increase even more our voxelization, our OpenVDB voxelization. So create more voxels and we would get a smoother result. Or we could try doing some other tricks. And for now, I would like to explore some other easy modifications to this simple setup we have here right now. So what I want to do is, I think we can get a better surface quality if we just not use only the center of a voxel. Maybe if we use and spread some points around the voxel space. Maybe up, down, left, right. So just randomly around the center point, I want to spread some particles and then use those more particles to just fill the gaps so that I do not need that much of a resolution for my volume. So how do we do that? So first thing is we definitely need some extra controls we want to have. And I would say we just use an input to control our number of particles we want to create per voxel. So keep in mind, I want to create more than one particle per voxel and spread those particles around. So I'll create an input with number of particles. When I press now compile, have a look here. And also let me just select it right away. We will see that we get a new input created. Number of particles, that's the input I create. And I have a minimum value set there, and number of particles starts with 1. So now I have a parameter I can work with and use to control the amount of particles we want to have. So the next thing is I need to a variation around my center of the voxel. So to get that, I'm going to have a variable declared. That's my diffusion around the voxel center. And there's a function I can use from our field input, field in voxel size. So that will give me how big is my voxel. That's my resolution I set in the beginning, these 1, 2, 3 or whatever. And I just say, okay, I want to spread out in all directions, half distance everywhere. So that's where I want to spread my extra particles around each voxel center. I'm going to spread around some more particles. So the next thing is when I'm going to spread out particles, I need to be careful that these particles are not outside my surface. So I just want to stick them really at the surface or around the surface. So we need to make sure that we're testing not only for inside volume. So I need to make sure that when I'm testing here, that we are actually testing a range so that I can grab my variations. So let me just swap this out. So what I did here is I use my field in and I'll check, okay, what's the value of the voxel? Because these are SDF fields, that means 0 is our surface, the exact surface position inside of the volume. If it's larger than 0, it means it's outside of my volume. And if it's smaller than 0, it means inside of the volume. So what I do here is I want to have a little bit of a wall thickness there, a range or an area I want to create my random particles. So that's my test, and we can continue now. So now I need to create the position variation. So I want to have a variation of my positions here. So the next thing I do is I declare these two variables to store a position and to store a distance from the point or the position. And now what I want to do is actually create a little for loop that will allow me, let me just bring that in here. So let me just do that here. I bring in this for loop. What I'm doing now is I'm using my number of particles. You remember we created this. So I run the amount of numbers I set here. And now I want to, inside of this for loop, I want to create a position variation. And we have functions for that already built in. So it makes it very easy, simple, straightforward. It's so dead simple. It's just really makes fun working with MEL. So I'm creating the position variation, and my diffusion around the point of the position is what we calculated up here. It's half the voxel size. So that's what we do here. And then I'll use the calculate the sample, get the information from the voxel, from the position. And then what I want to do is next, I'm not just creating the particle right away. I want a condition to create the particles, because we need to be sure now that when we create the particles, that the particles are actually close to the surface or inside our volume. So because we are doing a random position variation here, it could be that particles are outside our surface. And I don't want to have or see any spikes or bubbles or any weird things here. So what I did now, let me just remove this general creation. What I did here now is I create the particles only when I'm inside of the volume. So let me just restart the simulation. And here we go. We see already a difference. Let me just, for exploration purpose, turn off the surface dynamic set that creates our surface. And we can see we now have a random positioning of particles to spread out to help our surface, or at least that's what we want to achieve. So now I'm just creating one particle, so we are actually not really achieving anything. So I need to create some more particles in our loop, and we can already see with a few particles I can increase without changing the volume. Keep in mind, we're not changing the volume. I'm just creating really fast extra particles to fill the gaps in our voxel space. So this is just extra particles easily created without handling complex volumes. So let me just turn on the surface again. So now we are getting really much better representation of our volume. And yes, the oil tank looks strange, and I'll explain in a second what I did here, because when we look closer here, we can see something interesting going on. So what we have here is exactly this condition. That's what I said is our wall thickness. We want to make sure, so we are placing random particles there, and within this range we are going to create these particles. So now what we can do is, let me just cut this open, this volume. And there's also, and that's the beauty of MEL. I don't have to do complex node systems, getting a box, moving a plane or anything. I can just go in here and add this little tweak. I say, I'm only doing a particle or creating particles when they are inside the wall thickness and when my world position of the voxel, and in this case only the Y position, is greater than 0. What that means, let me just show you. The torus is centered to the origin. So only when Y, that's this direction, is greater than 0, I'll create these particles. Now when I restart the simulation, let me just restart the simulation by going back and forth. I'm just cutting off. That's what I'm doing actually, is I'm cutting off here at this origin plane, so to say. I'm cutting open the OpenVDB. And now you can see we have actually created with this little condition a wall thickness. And wouldn't it be great if we had an option to interactively control our wall thickness as well? Let me just bring back my thinkingParticles interface. And yes, we can do that. We can do that very simple and easy. Let me just let me just copy this and I'll create another input. Let's call this input wall thickness. And this is just a scalar. We don't need these restrictions because we can go to plus and minus, but anyhow, we have the scalar here. And now instead of supplying a value, I'll just say, sorry, we need to make that. We need to compile, create the input, wall thickness. And now I can just access the wall thickness in value. And the same here, the negative wall thickness in value. And now what I did here is I created another input for the wall thickness. And now if I change the wall thickness, I have, by the way, just if you didn't know, edit on the fly turned off. That means we have interactive updates. So whenever I change something in my MEL script, it will instantly update. And you can see now we can control our wall thickness in detail, just like so. So it's really easy and amazing to extend and expand that. And we could do the same for our cutting plane, for example. We could just, instead setting the value 0, we could have here a cutting plane distance and then, or y-axis or whatever we call it, and use that and interactively adjust our objects here. So to finalize this tutorial and wrap it up, let me just go back to the shape to volume. And let me do one more thing here. We'll increase just a tiny bit our resolution of the volume. And we can see right now when we do that, that our resolution is already much, much better. And let me just go back here. And we are doing a little bit more thickness. And now we get really a nice, just increase particles just a tiny little bit. Now we get these really nice objects here with wall thickness. I hope you enjoyed this little quick tutorial, and I hope you could see the power and the ease you can adjust and create your visual effects like no other tool on 3D Studio Max. Thank you for watching this video. Check out our other videos as well, and goodbye.